So we are working on sections 4.5 and 4.6. So 4.5, first we're going to talk about dilations. So a dilation is a transformation in which a figure is enlarged or reduced with respect to a fixed point C called the center of dilation and a scale factor, which is known as K, which is the ratio of the lengths of the corresponding sides of the image and pre-image. All of that is going to make more sense. Key things here, we're talking about dilations. Dilations make things bigger or smaller. Think about like your eyes, like your pupils when you go to the eye doctor. If you go into a really bright room from a dark room, your pupils will shrink or get bigger. And kind of the rate at which they get bigger or smaller, that's our scale factor. So if your pupils get twice the size, you'd have a scale factor of 2. Or if they shrink, if they become half the size, you'd have a scale factor of 1/2. Dilations are pretty straightforward once you kind of get the hang of it. So we have something called the coordinate rule, and this is sort of just putting dilation into like generic terms. So we're saying if some point P, it's at the coordinates xy. Okay, we don't know where that is, but just some coordinate xy. It's the pre-image of a point, then its image after a dilation centered at the origin, 0, 0, with the scale factor of K. Okay, so the big thing here, we had a point that's a pre-image at xy. It has a scale factor of K. So P prime, wherever x and y were, it's going to be K times x, or K times y. So this is just using it in generic terms. But again, this is going to make a little more sense once we introduce some real numbers. So example 1. They're telling us graph triangle ABC with vertices at those coordinates and its image after a dilation with a scale factor of 2. So I guess first things first, let's graph triangle ABC. So 2, 1, that's our A. B is at 4, 1. There. C is at 4, negative 1. All right, so there's our pre-image. And they're telling us to enlarge it using a scale factor of 2. So we're going to dilate it by a factor of 2. So the coordinates, whatever they might be, we're just going to take each of the coordinates and multiply them by 2. So if a point's at xy, our new point is going to be at 2x and 2y. So for example, I'm going to switch colors here. A is located at 2, 1. So if we multiply that by 2, 2 times 2 is 4. 1 times 2 is 2. So A prime is going to be at 4, 2. B is at 4, 1. So 4 times 1 is 8. Sorry, 4 times 2 is 8. 1 times 2 is 2. So B prime will be located at 8, 2. And C is at 4, negative 1. So 4 times 2 is 8. Negative 1 times 2 is negative 2. So C prime will be located at 8, negative 2. We can connect our dots. Okay. They tell us down at the bottom. So notice the relationship between the lengths and the slopes of the sides of the triangles in example 1. Each side length, each side length of triangle A prime, B prime, C prime is longer than its corresponding side by the scale factor. The corresponding sides are parallel because their slopes are the same. So what they're kind of pointing at here, look at side BC, for example, of the pre-image. So side BC, it's 2 units long. It's 2 units tall. We multiplied everything by 2, and now B prime C prime, this side, is 4 units tall. Same is true of this horizontal side, AB. It was 2, and now it's 4. The hypotenuse, whatever its length is, it's also going to be doubled. But do notice that like the sides AB and A prime, B prime, okay, like the top sides of both triangles are parallel to each other still. Okay, they're both running horizontal. And sides BC and B prime, C prime, okay, those are both vertical. So those are going to be parallel to one another. All right, let's flip it over. Okay. Scale factors can also be negative. They can be fractions too, which we're about to see. So when a scale factor is negative, the figure rotates 180 degrees. All right, they give us an example here. They say triangle FGH has vertices at 3, 6. F's up there. G is at 3, -3. And H is at 6, 6. They're pretty far apart from each other. Okay. There's our triangle. They want us to graph its image after a dilation with a scale factor of k equals -1/3. So I liked in the last example where they sort of had a table for us. So I'm going to try to recreate that table a little bit. So F is at 3, 6. G is at 3, -3. And H is at 6, 6. So we're multiplying all of that by -1/3. So F prime, multiplying something by -1/3, it's really the same thing as dividing it by -3, if you prefer to think about it that way. So 3 times -1/3, it's really the same thing as 3 divided by -3. So 3 divided by -3 is -1. 6 divided by -3 is -2. G prime. So 3 divided by -3 is -1. -3 divided by -3 gives us +1. And H prime, 6 divided by -3 is -2. That'll be another -2. So F prime is located at -1, -2. G prime is at -1, 1. H prime is at -2, -2. So just notice, our triangle shrunk by a factor of 3. Okay, we took the pink one, divided it by 3 essentially, and got this little black one. And because it was negative as well, it rotated it 180 degrees. It's kind of odd how that happens. So calculating scale factors, this part becomes, I mean, it's pretty easy, just the same as when you're given the scale factor. But I don't love the equation that they gave us here. So they say image length over actual length equals k. I prefer something like image length over pre-image length equals k. So if we maybe let's look at that previous example just to kind of illustrate what we're talking about here. The image length. So let's maybe look at side G prime F prime. All right, G prime F prime looks like it's 3 units tall. So I'm just going to throw a little 3 down here. And GF was 1, 2, 3, 4, 5, 6, 7, 8, 9 units tall. I honestly picked a bad example here. Since they do invert We'd want to make one of those numbers negative, but nevertheless, it reduces to negative 1/3. And that was the k in the previous example. So kind of a bad example, but let's look at some other ones here. So say you are using a word processing software to type the online school newsletter. You change the size of the text in one headline from 0.5 inches to 1.25 inches tall. What's the scale factor with this dilation? So take our image length. So just remember 0.5 is the pre-image, 1.25 is the image. So image length is 1.25 divided by 0.5. Throw in a calculator, and k ends up being 2.5. So that's saying we increased the original text height by a factor of 2.5. So we made it 2.5 times bigger, and that brought us up to 1.25 inches tall. Okay. Example 3. An optometrist dilates the pupils of a patient's eyes to get a better look at the back of the eyes. A pupil dilates from 4.5 millimeters to 8 millimeters. What's the scale factor? All right, so the image was 8. The pre-image was 4.5. We throw that in a calculator. It gives us about 1.8. So the pupil's got 1.8 times larger. All right, let's flip it over and move on to section 4.6. Here we are talking about the difference between, congruent and similar figures. So something we've kind of talked about a little bit, but not in specifics. So congruent figures, you should be familiar with them. These are figures that have the same size and shape. Similar figures, okay, so congruent figures versus similar figures. Similar figures are figures that have the same shape, but are not the same size. All right, so I don't know, I can give you a quick example here. We have two triangles, and everything about them is the same. We know that those two triangles are congruent. But if we have, say, another triangle, let's say it's a right triangle, and smaller right triangle, okay? Let's say these two are the same shape, okay? Their proportions are all the same. One's just bigger than the other one. So those two would be considered similar, right? So we have congruent shapes and we have similar shapes. The rigid motions, we have discussed these before. They're motions that preserve size and shape, such as translations, reflections, and rotations. So every one of the transformations we've talked about so far, they preserve size and shape. So you start with a shape, your final shape should be congruent to the original, whether we take that image and translate it, so slide it left and right, if we rotate it, or if we reflect it, that shape is going to stay the same size and shape, or that figure is going to stay the same size and shape. Compare that to a similarity transformation. All right, so this is really talking about everything we just talked about, okay, translations, reflections, and rotations, but it adds in dilations. So if we just take an image or a pre-image and dilate it, we will get a new figure that is similar to the original. Or if we have some kind of composition of rigid motions and dilations, it's also going to give us a similar figure. So if we're just doing the first three, translations, reflections, and rotations, it's a rigid motion, it's a rigid transformation. But similarity transformations, key thing here is dilations. It introduces dilations. Those are two different things. All right, let's do an example down here. So triangle ABC, it has vertices at 9, -6. That's A. B is at 0, -3. And C is at 3, -9. Your points, connect your dots, all the good stuff. All right, so this is a composition where our first task is to reflect in the y-axis. So B is just going to really state where it is. So B prime is same spot as B since it's on the y-axis. C is 3 units right, so we'll go 3 units left from the axis. And A looks like it's 9 units right. So on that same horizontal line, I'm going to go 9 units left to get C prime. Right. It's there. Now we need to do a dilation. So I'm going to get the coordinates of B prime. Oh, I made a mistake. That should have been A prime. So I'm going to get the coordinates of A prime, B prime, and C prime. A prime looks like it's at -9, -6. B prime is at 0, -3, and C prime at -3, -9. We're taking each one of those and multiplying it by 1/3, or dividing it by 3, however you like to think of it. So A double prime, B double prime, C double prime. All of them are going to be sort of 1/3 the size of the pre-image here. So -9 times 1/3, that's going to give us -3. It's really just dividing by 3. So -6 divided by 3 is -2. 0 divided by -3 is 0. -3 divided by 3 is -1. -3 divided by 3, it's going to give us -1. And -9 divided by 3 gives us -3. Okay, so we're taking this black triangle and sort of shrinking it by a factor of 3. So -3, -2, that's A prime, or A double prime, sorry. 0, -1, it's B double prime, and -1, -3, oof, didn't give myself all the room there. That is C double prime. All right, so just notice it looks like that black one just kind of shrunk. All right, I think we have one more example. All right, they want us to describe a similarity transformation that maps trapezoid WXYZ to trapezoid PQRS. So if I kind of look at it, I'm gonna do a little color coding here. So that orange ones are a pre-image. And it looks like there's a couple of things that happen here. Looks like we need to flip it upside down, and we need to dilate it. We need to kind of expand it a little. So reflection, I guess we're going to reflect it in the x-axis. And we could do that. Okay, if I guess W and Z are just sort of going to swap places, but I think if we flipped it, okay, Y would end up being somewhere in that neighborhood. And x prime would end up being somewhere down there. So if we flipped it over the axis, this isn't very scientific, I apologize. But if we flipped it, it would end up looking something like that pink trapezoid there. Now we need to figure out how much it dilates to be that final size. So if we look at the, what do we want to look at? It's not a very good diagram. I guess WZ, if we look at that side, looks like it's 2 units tall. And SP is 1, 2, 3, 4 units tall. So this is a dilation with a scale factor of 2. So it just became twice as large. And that is it for notes.